All right, example 4. If you're standing just off the side of the road and a police car is flying down the road at a very fast 40 meters per second with a siren going at frequency 800 hertz, if this and its siren is going at frequency 800 hertz. If the speed of sound is 340 meters per second, what frequency will you hear as the car is approaching? Once it passes you, what are the sounds that you're going to hear? So clearly, we're going to need to use the Doppler effect, right? Because the Doppler effect, our formula for that, gives us the change in frequency due to motion of the emitter, motion of the receiver. So in general, it was F equals V, speed in the medium, plus or minus V, speed of receiver, divided by V, speed in medium, plus or minus V, emitter, times the frequency emitted. And remember, it's up to us to figure out pluses and minuses and all those sorts of things. So just to mark everything off from the beginning, velocity here, speed of our medium, 340 meters per second, right? That's the speed of sound here. Car is flying down the road at 40 meters per second, so the emitter is moving at 40 meters per second. The receiver, is the receiver moving? No, you're just standing there, so you've got 0 meters per second. And finally, frequency emitted is equal to 800 hertz. So in the case where the cop car is going by you, you're going to have your frequency that you're going to hear is going to be equal to V. Now, what do we want to use? Do we want to use plus or do we want to use minus? Well, if it's moving towards you, if you were moving towards it, you could look at it from either point of view, right? If the two things are moving toward one another, then you're going to get more, right? It's going to go up because the two objects are moving towards one another. So it's going to be V plus V receiver, right? Because you're going to be increasing it as you move towards those wave fronts. So these two objects moving towards one another divided by V plus or minus. Once again, the emitter is coming towards you, so you've got more wave fronts coming at you, so your frequency is going to go up because it's packing those wave fronts at its front. So are you going to use plus or are you going to use minus? Remember, smaller denominator means bigger overall number, so you actually use minus VE times the frequency emitted. We've got V, so 340. Your speed is 0 divided by 340. Its speed is 40 times 800. 340 over 300 times 800, we've got 906.7 hertz. Great. So that's what you'll hear as it moves towards you. Now, just after it passes you, once it passes you, it's going to be going the opposite, right? It's going to be going very differently than it just did. Change up the color. So you're standing here, but now the gulf between you two is widening, right? You can effectively think if you're moving away from it, it's moving away from you. So now we're going to actually have to use a slightly different version of this formula. So all of our constants just stayed the same, right? But it's the way that the formula changes with those pluses and minuses that will give us a different experience. When it's coming towards you, you're going to hear a higher frequency than it naturally emits. When it's going away from you, you're going to hear a lower frequency than it naturally emits. So if frequency is equal to V plus or minus VR, which does it become? Well, if you're moving away from an object, you're going to cause yourself to experience less wave peaks because you're going to be running away from the wave peaks. So if you're running away from the wave peaks, we need a smaller number up top, so V minus VR, divided by, now the emitter, is the emitter going to be getting fewer? Is it bunching up or is it spreading out them from the point of view of the receiver? Well, it's spreading them out because it goes farther away before dropping the next peak. So that means that we're going to have a smaller frequency. It's going to contribute to making a smaller frequency. So it's V plus VE because it's making a larger denominator times the frequency emitted. So we get 340 once again minus 0 divided by 340 plus 40 times 800 equals 340 over 380 times 800. And that gives us the value of 715.8 hertz. Great. So when it's moving towards you, you get 906.7 hertz. of frequency. When it's moving away from you, you get 715.8 hertz. And if you were just standing still while it was sitting still next to you, if you were both still next to one another, you'd hear 800 hertz. Or alternately, if you were the cop in the car, because you're moving with it, you're moving at the same speed, so to you it's as if it's effectively still, it's going to be 800 hertz for the cop in the car the whole time. So, if you're curious what these sound like, because frequency actually is what is going into our ears, if you want to know what this was, and keep in mind a siren isn't going to sound just like a pure tone. We made this a little bit easier by saying it was just giving out a single hertz, and we'll talk a little bit more about how sound is actually working out after this example, but let's actually listen to it. So I've got an example sound here. So here's an example sound. I'll be played in just a few moments, and the first sound you're going to hear is the 800 hertz sound, just to give you a sense of what 800 hertz sounds like tonally. 2, you're going to hear the 906.7 hertz, what it would be as it approaches you. And then 3, you're going to hear 715.8 hertz. And then finally, 4, you're going to hear a simulation of what it might sound like to have it drive past you. Because remember, it's going to actually, at some point, swap between these two. And if it were driving directly at you, it wouldn't ever swap until it went through you. But because you don't get hit by the car, hopefully, you're actually going to have this period of time where it's going to slide between the two, where it's going to slide between the high frequency to the low frequency, or from the low frequency to the high frequency, as it passes you or as you pass it, depending on the situation. It's going to slide frequencies because you are actually not going to be passing directly through its point. This works reasonably well when you're close to the path that it's taking, but since you can't ever actually be on the path and not get, run over, you're going to actually hear a change when it's passing. Say, when it gets here, the wave changes is going to be about on the distance. In the extreme, we can effectively treat it as a straight line, but when it gets close to you, there's going to be a change in the way the velocities are working. We aren't dealing with that because that's much more complicated, but that's why it slides when you hear it in real life. And I'm sure you've heard a car siren or something go off that has moved by you quickly while it's been emitting noise, and you've heard this consistent slide sound, and that's what we're going to hear here. So finally, we'll hear a slide from 906.7 that will start at 906.7 hertz. It will go on for just a little bit, and then it will slide down to 715.8 hertz. And this gives you some idea of what you might actually hear. All right, so ready for that example sound? Go. All right, sounds pretty good. So there you go. There's an idea of what it sounds like. Now, keep in mind a couple of things. Real sounds in real life aren't just pure tones. Those that you just heard now was a pure tone. It was a pure tone of 800 hertz. It was a pure tone of 906.7 hertz. But in real life, you aren't going to actually hear pure tones because there's many, many tones. If you hear an actual cop car siren, it goes way between all these different things, right? It's trying to catch your attention by sliding through a huge variety of tones. So in real life, we hear many, many tones at once compacted together, interacting with each other, which is actually how we experience light, too. So the way we experience is different than just breaking it up into single values that we'd get here. But this still gives you a good idea. It's much easier to work with these single values, right? It'd be hard to describe the whole range of possibilities, which is why, when we get to a very high level in physics, once you are really trying to describe it as opposed to just understand what's going on fundamentally, which this does, it gives you the chance to understand it fundamentally, it gets hard to deal with all of the things happening at once. So in real life, there's many frequencies going on. There's many things happening. The real sound is compounded by a number of things. It doesn't just directly switch between these two. It slides by you. The angle that you are from the car, the distance that you are from the path that the car is taking as it goes by you, if maybe it turns around you as it goes by, all these different things will change the sounds that we'll hear. But this is one possibility that gives you a reasonable approximation of what it's really like. All right, I hope that made sense. I hope waves are beginning to come together. It's a huge can of worms that we've opened, and we only have a little bit of time to experience some of it, but there's so much more stuff in waves that we could talk about and go in depth, but we're just sort of scratching the surface so we can at least get an idea of what's going on here before moving on to the next thing. All right, hope it made sense, and I'll see you in sound, which will be a great use of this stuff that we've just been talking about. Bye.